optimization. That's the first thing I want to get done. And I've got a kind of little note to self here to go over some of the questions. There are a lot of different puzzle questions that you can get, and these are just a little taster of them. First one I'm going to do is a version of question 3. So I've wrote the whole thing down here. What is the maximum vertical distance between the line y equals x plus 30 and the parabola y equals x squared if you choose values of x between -5 and 6? So if you imagine, sometimes it's a good idea to draw a little sketch. Doesn't even need to be that accurate. If you imagine this being the straight line, y equals x plus 30. I'm only interested in it from x equals -5, so I'm going to pretend that's x equals -5, and it finishes at x equals 6. So that's that bit of it. And you have a quadratic, y equals x squared, looks something like that. Right. And we are being asked to find what's the maximum vertical distance. So if you can imagine, if you took any value of x, the vertical distance they're talking about is from there to there, right? Now, I did not make this accurate, so there's no guarantee that that's the case, but it looks to me that it would probably happen right at the end. Would you agree? That distance is probably the biggest. So we are going to do calculus to find that. So my optimization function is basically, well, I'm going to call it y, and it is going to be x squared take away x plus 30. Or I can have it as x plus 30 take away x squared. Would you agree both of them are finding the distance between them? Now that I've wrote that second one down, I kind of like that one. Just looks easier to do. So once you have got a function that you're trying to maximize or minimize, what I'm going to do now is differentiate it. And look for critical numbers, because the solutions almost always exist at the places where the derivative is 0 or when the derivative is undefined. I don't even need to look at that one because I know that's never undefined. If I want to find out when the derivative of this optimization function is 0, I can do it in my head. So would you agree it's x equals 1/2? Now, is 1/2 inside my range? Yes, it is. So I should be able to find out what that value is. What is the maximum vertical distance? It's the value of the function at 1/2. So it's 1/2 plus 30 take away 1/2 squared. So that's 30 1/4, which is 121 quarters. So evidently, that shows you how bad my sketch is. Round about x equals 1/2, the distance was at its maximum. So I'm going to go into Desmos now and find out what the real shape looks like, rather than that just I drew whatever seemed appropriate. Well, according to Desmos, we have a guy called y equals x squared. Nothing special about that. We have a y equals x plus 30. Should be a straight line. Okay. Probably just, oh, I can adjust my windows here. Cut a little bracket. We want -5 less than or equal to x less than or equal to 6. Finish off my little curly brackets. There we go. So, what else can I do to make this prettier? Maybe I could make the x's just go from -5 to 6. There. And allegedly, at this point here, that's a maximum distance. Does that seem reasonable? Yeah. But if I asked you only with that picture, would you agree it'd be quite hard to tell? You'd be able to say, well, it looks somewhere like from somewhere between here and here, right? One of these distances might be the biggest. It's definitely not up here, right? That's quite close. Definitely not up here, right? That's quite close. So somewhere in the middle. But calculus told me exactly where, right? At x equals a half. And so we've solved that puzzle. Now, I don't want you to try and think of solving this as, oh, that's how you do this question. Because optimization questions are so different. There's so many of them. What you've got to think about is, what function am I trying to maximize or minimize, right? What we're calling the optimization function. For instance, in question 6 and 7, they give you the function. So we have a function, this one here, this one I'm picking, I think it's 6. And they tell you that the yield that a crop gives when you put n amount of nitrogen into it is given by this formula. And you're told that K is positive. And we're being asked to find the level of nitrogen, so find N, that maximizes the yield. Right. So you can imagine a farmer's going to put in fertilizer. That's probably where the nitrogen's coming from, I'm assuming. Or maybe it's just nitrogen on its own. And he can put a lot in, and as he does it, the yield will go up. But won't there be a kind of, if he keeps dumping more and more, it's going to be no benefit. In fact, it might harm the plant. Too much of a good thing is bad as well. So there's a kind of sweet point. If you know the function, this is the simplest one. I have my optimization function, right? In that previous one, didn't we have to create it? And we're more than likely going to have to create most, but not this one. So here's our guy. I'm going to differentiate it with respect to n. Now, k is just a constant, right? It's just 42, right? So treat it like a number. That's what a constant is. So in this case, that's f, that's g. So I'm looking at a quotient now. So once you've got the optimization function, differentiate it, and then find the critical numbers. And the critical numbers are going to be where your answer lies, right? Typically, at least. So let's see what the derivative looks like. If you differentiate kn with respect to n, you get k. You leave g alone. Take away, you leave the top one alone, and you differentiate the bottom. And then the whole thing in the bottom gets squared. And then style points will kick in here. I'm going to distribute. Looks like I've got a 25 take away a kn squared over 25 plus n squared squared. Okay, so I've now differentiated the optimization function. And we've got to find its critical numbers. right? And they'll tell me the value of n where the derivative is 0 and the value of n where the derivative is undefined. So we're going to get the critical numbers. So the derivative here could be 0. The other possibility is that the derivative is undefined. That might be where our solution lies. Well, that fraction is only going to be 0 when the entire bottom is 0. And 25 plus n squared is never going to be 0. So there is no undefined to look at in the first place. If you want a derivative to be equal to 0 and it's a fraction, then you only need to focus on what makes the top 0. So I don't care what the bottom is, it won't matter. Okay. I need to solve for n here. As long as you do it to both sides, it's okay. So what would you like me to do to both sides to solve for n?
Subtract 25.
Okay. Sounds like a plan. What are you going to do now?
I was going to say start by multiplying both sides by -1.
That also would work. Since we're here, let's do your -1. It's not the only way to do this, but they're all going in the right direction, so it doesn't matter. What's next?
Divide by k.
Yep. Put it up here because we're running short of room. Okay, what's next?
Square root of both sides.
Right. Now, since n is a thing that you put into the ground, can we make the assumption that it's positive? So I'm only going to take the positive square root. And then to make it slightly pretty, I could do that. Or if you want to be really, that's fine. So 5 divided by the square root of k, whatever k happens to be, is the optimum value of nitrogen that will maximize the yield. So if you tell me k is 100, just for argument's sake, right? K is 100, then you will do 5 over 10, you will do a nitrogen level of 50% or something, or 50 units. And that's it. Right, that's quite different from what we did on Thursday. It's quite different from that one. I think each question has its own kind of look to it. The next kind of questions I'm looking at here are fields, boxes, and building pipelines. And that's kind of where we're going to go next. We're going to do a question, I think, next is going to be involving rectangles again. And rectangles in farmers' fields. So we're going to find one. Yeah, this is a version 8. And I'll just read it to you. It's a lot of information. Consider the following problem. A farmer with 850 feet of fencing. So I'm writing that down. 850 feet of fencing. He is going to enclose a rectangular area that is then divided into 4 pens with fencing parallel to one side. So now it's time to draw rectangles. And he said he's going to do a rectangular pen split into 4 with them parallel to one side. So there is the picture that they've just told me. And we are being asked to find the dimensions of this rectangle that maximizes the area. So we're being asked to find the dimensions of the rectangle that maximizes the area. Okay. I don't know what that distance from there to there is. I'm going to call it X. I don't know what the distance from there to there is. I'm going to call it Y. That's a good starting point. Basically, isn't X the length and Y the width? So when they talk about the dimensions, they want to know what number X will be and what number Y will be. Now, the optimization function is the area. So the area is X times Y. But I don't want an optimization function to have two variables. I want it to have nothing but X's. That means I have got to find a way of changing that Y into a function that uses X's. And the way I'm going to do that is by using that fella. So I'm now going to move over and solve that problem. If you want to build this rectangular thing with four guys going this way, then the perimeter, I'll call it that, the amount of fencing, is going to be 850. That's made up of two pieces of length X plus 1, 2, 3, 4, 5 pieces of Y. And so that must add up to 850. Does that make sense how I got the relationship with X's and Y's? That the 2 X's plus the 5 Y's is how much fencing he needs, and I know it equals 850. I then solve for Y. I'll take away 2x from both sides. I will then divide both sides by 5. I now know what Y is in terms of X. So I go here and I go X times negative 2/5 X plus 170. And if we can get to this line here, you've broken the back of the question. This is what we call the optimization function, right? In this case, the thing that you want to make as big as possible. I could have left it like that and it's fine. I could have done a product show, but I'm going to distribute it. There, that's the optimization function. So what do I need to do now is differentiate it with respect to X. That's negative 4/5 X plus 170. And then I need to find the critical numbers, which in this case is the value of X that makes the derivative 0. I do not need to go looking for undefined because there aren't any. And what I've left with now is an equation to solve. And this is where I'm going to stop. I know this isn't the right answer, but just for argument's sake, let's suppose X was 50. Right, just for argument's sake. Your question was not to find X. Your question was to find the dimensions of the rectangle. So what you would then do is say, well, the length is X, so that's 50 feet. And the Y, which is the width. Well, if you want to find Y, don't you have to put that guy in there? So you put in whatever I said, 50, and you put it in and you calculate it and you get Y. What would that be? If it was 50, it would be 150. Okay. And that would be your answer. Length is 50, width is 150. You are good to go. Now, in case some of you are wondering, but you done these guys vertically, you didn't do them horizontally. Would it make a difference to the answer if I did the rectangles, you know, the lines going this way? No, it wouldn't. You still would have got these two guys. They may switch places. You know, you might call the width 50 and the length 150, but that would be the only difference. Any questions about that one? Got a story, build a picture, figure out using this piece of information what y is in terms of x. Take your function, in this case that you're trying to optimize area. It might start life off as using two variables, but eventually it will turn into just x's. Once you've got it done, differentiate it, find critical numbers. And that is one of the rectangular field stories. And there's another one, I think it's 11. Okay, a farmer wants to fence a rectangular plot of land adjacent to a wall. So here is the wall. And here is going to be the rectangular fence. Do you see that he only needs 3 sides because he's using the wall for free? Right? He doesn't need to put in there. So that's the beginning of the story. And it says no fencing is needed along the wall here. That's good. Now they tell me that fencing costs $20 per foot. Okay. And the farmer is only willing to spend $8,000 on fencing. And we're being asked to find the dimensions of the field. That would enclose the most area. That's the clue to the optimization function. I did not know what this guy is. I'm going to call this distance x. I'm going to call this distance y. So the optimization function is just going to be x times y. I need to figure out what y is in terms of x. Well, what do I know? I know that the fencing costs $20 a foot and there's $8,000 to spend on fencing. So if you take $8,000 and you divide it by $20 per foot, isn't that just a disguised way of telling me you get 400 feet of fencing to work with? Right? $8,000, $20 a foot, $400, 400 feet, I should say. Now, what do I know? Well, if you wanted to build this, the perimeter, I would call it 1x and 2y's. And it would come to 400 feet. And if you subtract an x from both sides, and then divide both sides by 2, that's the guy you need. So area is going to be x times 200, take away a half x, and that's going to be 200x, take away 1/2 x squared. And then you find the derivative. Wow, that's an easy one. And then you find the critical numbers. I can do that one in my head. It's 200, which means that guy's 200, and these two guys are 100. And that is the dimensions that will get you the biggest area of fence. Now, if the question had been find the dimensions, the answer will be length is 200, width is 100. If the question was find the maximum area, then I would only be writing one number down, and that would be the length and width multiplied together, in which case the answer would be that. So if they want the dimensions, the answer is length is 200, width is 100. If they want to know what the maximum area is, it's a single number, 20,000. If they want to know both, because sometimes they do, you tell me that, and then you tell me that. So read what's being asked, so you know, is it these two numbers, or is it that, or is it everything? Any questions?
I guess I'm slightly confused. Where do we get the 100 for
The
Y?
width?
Where do
Ah,
we get 100 for Y?
get it from here. So I know it's 200, take away a half times X, and that gets me Y. So it's 200, take away 100, gets me Y, and that's 100.
Okay, no, that makes sense. All right, thank you.
Yeah, actually, because the numbers were that nice, I just said, look, if that's 200 and I'll get 400 to play with, there's 100 left for each side. So I just did it in my head as well. Any other questions? Okay. I think there's another rectangle fence story floating about. Yes, okay. So there's another one. What's this one? This is version 10. Ah, this is where numbers keep in. Yeah, I remember this one now. A farmer wants to fence an area of 24 million square feet. Yikes. The area is 24 million square feet. So I'm going to draw my rectangle right away. And that's going to be X, and that's going to be Y. What's he want to do with it? And he wants to divide it in half. Okay. And oh, they take you through the steps, but basically you want to minimize the amount of fencing. Normally, you know how much fencing and you're trying to maximize the area. But in this case, you know the area and you're trying to use the least amount of fencing to make this happen. So since you are after essentially a perimeter, this shape is made up of 2 X's and 1, 2, 3 Y's. So far, so good. Now I need to find out what Y is in terms of X, because my optimization function, which is this guy, needs X's. So what do I know? Well, I know the area of this rectangle is X times Y. I know that the area is the ridiculously big number of 24 million. And if I divide both sides by X, there's my Y. So P, the total perimeter, the thing we're trying to minimize, is 2X plus 3 lots of this guy. And that's 72 million over X. Mathematics doesn't really care how ugly numbers are. I know they're really a pain to keep your head on. You know, that's huge. But couldn't that have just been 7 over X and then mathematics would have looked pretty much the same? So here is the goal. Find an optimization function. Find the guy you're trying to minimize in this case. We then differentiate with respect to X. And this guy's 2. And this guy is negative 72 million over X squared. And you just check that out. Call that X to the -1 and do the power rule. You'll get this. So we are looking for critical numbers now. That's when the derivative is 0. And when the derivative is undefined. Question?
Yeah, how did we get X squared?
This guy from here, right? If you differentiate enough fractions in your life, you will eventually just realize that 1 over X gets you that, right? So if I wanted to do the derivative of 72 million over X, if I wanted to do it the long way, I would call it 72 million X to the -1. If you differentiate, you multiply by the power. And reduce the power by 1. You then take the thing and make it look pretty. And that's where my X squared came from.
Okay, I got it.
Sometimes you just get used to certain things and you cut out the middleman, right? You've seen it so many times. Now, undefined does exist. In this question, would an undefined happen when X is 0? Agreed? This function is undefined. This derivative function, you cannot calculate it when X is 0. Yes, this exists, but is this the solution to my problem? Well, in a way, this is silly, because if X is 0, doesn't the rectangle disappear? And so we are going to throw that out as a non-usable possible solution. On the other hand, this horrible thing could be, and it will be, equal to 0 somewhere. So what you have to do is you have to solve a rather ugly equation. Which is the derivative, this guy, equals 0. Okay. As long as you do it to both sides, it's okay rules, right? So tell me what to do to both sides. There's more than one way to do this.
The easiest way that I do it is I would add 72 million divided by X squared to both sides.
Good start. Where
And
are we
then-
going now?
And then multiply both sides by X squared. Divide by 2.
And where next?
Square root.
Square root both sides.
Right. In this case, only the positive square root. Only the positive square root makes sense. When you're getting negative 6,000 feet, doesn't really make sense in the context of this question. So I now know that X is 6,000 feet. I need to know what Y is. I guess I'll call that the length. And now I need to know the width, which is what Y is. Well, to get Y, we use this relationship. 24 million divided by X. And I believe the answer you get is 4,000 feet. So if you want to build this rectangle split in the middle with an area of 24 million square feet, right, and you want to minimize how much fencing, right, that it would need to do all the things you wanted. If you make X 6,000 and Y 4,000, right, so if you make this distance 6 and that distance 4, you will be able to do all the things, right? You've solved your problem. Any questions? So even although that was a rectangle question, didn't the math look a little bit different? Because one, you knew the area and you were trying to minimize the fencing, and the other, you knew the fencing, you were trying to maximize the area. They were similar, but not quite the same. So we have two more kinds of puzzle questions to kind of do. One of them, one family of them, are ones involving boxes. So let me start off with a very simple one. The box will have a square base. Okay, so I wish I hadn't done that now. Yeah, I'll do it over here. There's my box. Since my box has a square base, X times X, and it'll have a height, Y. So this is a box where all 6 sides are present. That's the first kind of box question. And I'm going to give you something to minimize or maximize. You have, what should we do? You know that the volume of this box is 64 cubic meters, right? So you're told that. And we want to minimize the amount of material to build it. So if you imagine you were going to build this box, say, out of metal, right? And the box has to have 64 cubic meters because that's what you need. You could have all sorts of different shaped boxes with a square base. Couldn't you have a little skinny square base and a very tall rectangle, right? Or you could have quite a flat, big one and not very high, right? We have to figure out what the dimensions are, right? What X and Y are that minimize the amount of material. So I'm going to call this guy A for amount of material. Now, in this picture, the top of the box is X times X, which is X squared. Would you also agree that the bottom is X squared? So that's 2X squared. Now, there are 4 side panels on this box, right? Vertical panels. And isn't each one of them going to be X times Y? Won't that be their area? Right? So X times Y, and there's 4 of them. That is my optimization function. That is the one that I want to minimize, right? Of course, not uncommon is that there are Y in this formula. We don't like Y's in formulas. So I'm now going to use the fact that I know that the volume is, and it's 64. And if I want to find the volume of this box, it's length times width times height. which is x times y, which is x squared y, and divide both sides by x squared. There you go. Do you see how I found y in terms of x? By using the one piece of information they gave me that had the number in it. So the amount of material is going to be 2x squared plus 4 times x times y. And that guy times that guy gets you 256 over x. So far, so good. Now, you know what's going to happen next, don't you? We're going to differentiate it, critical numbers, solve it, right? If you differentiate it with respect to x, you'll get 2x. Can you trust me? Because I've done enough of these guys to know that that's what the other guy's going to be eventually. So we now have a derivative. Critical numbers are going to happen when the derivative is 0 or the derivative is undefined.
Professor, when we derive 2x squared, is it 4x?
You're right, it was. Well cut. Right, this fella here, undefined. Yes, it does happen. It happens when x is 0. And aren't I going to kill that off as a non-usable solution? Because if x equals 0, the box disappears into the universe, right? So I'm only going to focus on what makes the derivative equal to 0. Very similar, isn't it, Keith, to the one you did, you talked us through last time, right? Mathematical. Right? So I'm just going to kind of zoom through this a little bit. Multiply both sides by x squared, or if you're a cross multiply person, you get the same result.
I've got a question.
Yes.
So back to the page on the left, how did we go from a equals 2x squared plus 256 divided by x to 4x minus 256 divided by x squared?
I differentiated it. So power rule
Oh,
for x, power rule.
okay.
Okay. So what we got here is 64. Cube root of that is 4. And so x is 4, which means this guy is 4 and this guy is 4. And y? Well, if you take y is 64 over x squared. He is 64 over 4 squared. He is 64 over 16. He is also 4. And guess what? That's a cube. So if you want to minimize the amount of material that you need to build a box that has a square base, it looks like it's a cube. Well, that is box version number 1. Isn't it kind of the farmer doing the rectangle and you end up with a square? That kind of story. We're now going to do a different kind of box question. And I'm going to keep the same numbers. So this is going to be a volume as well. And it's going to be 64 cubic meters. Along with that. And we also are going to have square base, right? So it's going to be that guy. But there's going to be a difference. It's going to have a square base, but no top, right? So it's basically it's like a box without a lid, right? No lid, no top. And we are trying to minimize the amount of material to build the box. Now, since I've already got a lot of what we need already set up here, I'm going to call this X, I'm going to call this X, I'm going to call this Y. That's fine. The area, the amount that I need to build this box, that's where the difference is. When you had a lid, wasn't it 2x squared plus 4 vertical pieces? If you have no lid, isn't it just going to be a single x squared with 4 vertical pieces? Not a lot of difference, agreed? Now, since I've kept the volume the same, won't y still be 64 over x squared in both situations? What, question?
No, I was saying it should be.
Should be, agreed, yeah. Now, not a lot of difference, but there's going to be a difference in the solution. Remember when we had a complete box, everybody ended up being 4. The minute you take the lid away from this problem, doesn't the story change a little bit? So it's not going to be a cube. When I solve this, it's not going to be a cube. Right? It's not going to have all 3 dimensions the same. Do you think the box is going to get taller because there's no lid? Or do you think it's going to get smaller because there's no lid? What's your gut feeling?
Taller.
Okay, let's find out. So I will now differentiate with respect to x, only this time it is 2x. Oops. But everything else is pretty much the same. Now find the critical numbers. The only ones I'm interested in are the one that makes the derivative 0. So I'm trying to solve that guy. I'm not going to bother about the x equals 0. It's the same reason as why you can't have x equals 0 here, right? X equals 0 makes a box disappear. So undefined isn't important. If you add 256x squared to both sides, cross multiply, divide by 2, and x is the cube root of 128. That wasn't quite what you were expecting. And y, well, it's 64 divided by x squared, which is the cube root of 128 squared. So that's 64 over, well, I guess I should try and simplify the cube root of 128. It can be written down as a cube root of 64 times 2, so it ends up being 4 cube root of 2. Okay. So 4 cube root of 2. So x can be written as 4 cube roots of 2. And if you square this guy, you get 64 over 16 times the cube root of 4. And that gets you 4 over the cube root of 4. It's ugly, but it's the answer. I don't know if that's taller than that. I guess I could find out by finding out what numbers these guys are. So if you do 4 times the cube root of 2, it's about 5 and a bit. And if you do 4 divided by the cube root of 4, it's 2.5. Ah, so it's essentially half the height. So why would that work? Oh, if you don't need a lid, can't you make the base wider and get more area times the height? Yeah, it went down the way. Not obvious, but it did.
I got a question.
Yes.
So when we squared 4 cube root of 2, how did we get 42, or how did we get 4 inside the radical?
Here? This guy here?
Yeah.
Right. If you take the cube root of 2 and you square it, it's the same thing as the cube root of 2 squared, which is the cube root of 4.
Okay.
You can think of it as the cube root of 2 times another cube root of 2, which is the same thing as the cube root of 2 times 2, which is the cube root of 4. You can think of it like that as well. So essentially 5, yeah, what would that be? 5 times 5 times 2.5. Interesting. And the last question, oops, that I want to deal with is building a pipeline story. So here we go. Imagine off the coast, off the east coast of some land. This is land over here. Right? You have an oil rig, and you want to pipe the oil to the shore. And you have a refinery, which I'm going to put down here. And you want to build a pipeline. And there are essentially going to be 3 options. Option 1 is you just build a pipeline straight to the refinery, which you might think would be the easiest and simplest solution to this problem. But there is a problem to do with cost. Pipe in the sea. If you are doing a pipeline in the sea, it costs you 10 million a mile to do it, right? Whatever, right? 10 million. Well, that's one possibility. Could do that. Second possibility. Couldn't you just take the shortest distance to land? That's here. And then build 2 pipelines. One on the sea, right? And the rest on the land. So let's put in some numbers. The oil rig is 4 miles from the sea. And the distance from here, if you went all the way down that way, let's make that 3 miles. Now, if you do a pipe on land, it only costs you $6 million per mile, right? Because don't you, you only need to dig up the land, stick the pipe in, cover it up, right? Whatever you do with pipelines, I'm not a pipeline expert. And that is the second possibility. Right? So possibility 1, direct. Possibility 2, go here and here. But there is this third possibility, isn't there? The third possibility, it's going to be a bit hard because I don't have enough different colours. What else have I got in? Purple. Okay. Couldn't you go to some point here? So you'd build a little bit more on the sea, but wouldn't you also get a little bit less on land? So the question is, where do you build the pipeline? Do you build it at A? Do you build it at C? Or do you build it at B? And whereabouts should B be to minimize the cost? Yeah, for instance, it might be halfway, right? Halfway between here and there. Maybe it's a little bit closer to A, maybe it's a little bit closer to C. Maybe it's none of those. Maybe the cheapest is straight line. Maybe the cheapest is that one. Would you agree it definitely isn't cheap to go up the way to travel further, right? So I'm not even going to include that as a possibility. Would you agree everything is in this little triangle? So being the fanciest one, we have to set up our story. So I'm going to do each situation. Situation one is the direct line. Well, let's find out the cost. I need to know the length of that pipeline and multiply it because it's all on the sea by $10. So it's going to be $10 million, 10 of them times that length there. I'm going to have to call this guy D then. So it's DC. Now, if you build a little baby right angle triangle, don't you know that guy's 3 and that guy's 4? So won't that guy be 5 miles? You agree? Direct line, 5 miles. So that's going to be 10 times 5. That's going to be 50 million. So 50 million, just build a pipeline straight to the refinery. Situation 2. Situation 2 is going to be, you go from DEA and then you go from A to C. Right, so it's this one here. Now what will that cost look like? Well, it's going to be 4 miles at 10 million a mile plus 3 at 6 million. So that's 40 plus 8. That's 58. So that's 58 million. Okay. Now that I've found that one, can I cross it off my list? So right now, the cheapest way seems to be just to go straight from the oil refinery, or the oil rig to the refinery. So now the one that involves calculus, which is situation 3. And I'm just going to redraw my picture now. Let me do that again because I put the line in the wrong place. There's A. There's C. 3 miles. There's the oil rig at D. And we're going to go to some place here. And then we're going to go down here. And I am going to call this guy, what letter of the alphabet? E. So I'm going to call that distance X. I wish that 3 wasn't there, it's a distraction. Right. Going to call that distance X. Put the 3 over here out of the road. If from A to E is called X, What is the distance E to C going to be called using x's? So I'm telling you that distance from here to here is x. How much is it from here to there? If the total distance is 3.
3 minus x.
Now, I need to know two numbers. I need to know that distance and I need to know that distance, because won't the cost be how much to build this bit plus that bit? So our optimization function is going to be the cost function. And it's going to be the cost of going from D to E, that's the C bit, plus E to C. And these have to be in terms of X. Now, the one that's E to C is on land, so that's 6 times 3 minus X. And DE is in the sea, so it's going to be 10 times, right, that distance there. So what I'm now going to have to do is build a little right angle triangle. I know that distance, it's in our story, it's 4 miles. I know that distance is X. So shouldn't I be able to get E to D? And if you use Pythagoras, E to D squared will be X squared plus 4 squared. The distance ED squared, ED is going to be the square root of that. And so that is our optimization function. You agree that is one ugly looking function, but that's it. This is basically the cost to go by sea plus the cost to go by land. Multiply it out and convert it into the format that we need for differentiation. Now I'm going to differentiate with respect to x. Multiply by the power, reduce the power by 1, and then remember it's a chain rule, so finish with the derivative of the inside function. Differentiate that guy, you get 0. Differentiate this guy, you get -6. So this is going to be 10x over the square root of x squared plus 16. Take away 6. There's our derivative. We want to find critical numbers. We want to find when is our derivative 0. I know it's not going to be undefined just looking at it. So we are trying to solve that guy. Something really interesting is going to be coming up here. Anybody got a gut feeling where you should put that? Right, you've got 3 mile to play with. Do you think you should just stick it at A? Nah. If you stick it down here, isn't that just a direct line? If it was going to be somewhere between here and here, do you think there's a sweet point that you might be able to find? Any gut feelings? Do you think it's going to be quite close to here, quite close to A, or kind of in the middle? Any gut feelings?
Closer to A, I think.
I don't know. It's a short answer. I think I know what's going to happen because in some situations it does, but actually it might not end up the way I think it's going to end up. I think it's going to end up being a direct line. In other words, x is just going to be 3, which is what a direct line would be. And the reason I'm thinking that is just that I get a feeling that the pipeline on the sea isn't that dear, right? 10 compared to 6. That's the only film. And I'm just as, I don't know. I've just got a gut feeling it might do that. So if you add 6 to both sides, you get that. Now I'm going to do my own version of this. I'm going to cross multiply. And I'm going to divide everybody by 6, which is 10 divided by 6 gets me 5/3. Right, I'm looking at that stage now. Need some inspiration here. What do you think I need to do to both sides to solve for x?
So I think what you need to do here is divide both sides by x, which would be the square root of x squared plus 16 over x. But then if you square x in the denominator, it would be the square root of the quotient of x squared plus 16 over x squared.
Interesting. I'm not saying that's wrong because it might well be true, but that's not the way I'm going to do this one. I'm going to do something to both sides, but not quite the way you were talking about, Kate. I'd have to think about the way you described, how that would eventually solve. And if you're doing it that way, that's great. You can tell me if we get the same answer in a minute. But I'm going to tackle this a little bit differently. Any suggestions about what I might do to both sides that wasn't the way Keith was saying? Right. I tend to look at puzzles as what bit is causing me the most trouble and figure out how to get rid of it. The bit that's causing me the most trouble is this square root. I wish it wasn't there. So I'm going to square both sides. And if you square this guy, you get that. Okay, so squaring both sides. 5/3 x when you square it is this guy. Okay, what should I do next? I got you, Robert. What you thinking?
Subtract x squared from both sides.
Okay, which is basically subtracting 9 from this side. Agreed? 1x squared leaves you with 16 ninths. Okay. How about multiplying? Well, how about dividing both sides by 16 ninths, which is the same thing as multiplying by 9/16?
Question, how did you?
Yes. Question.
how
How
do
did
you-
I?
When you subtract 16 from both sides,
Yeah.
I mean x squared from both sides, how does that take you?
No, I'm
to-
taking 9 away from both sides. Oh, how? Right. Rewind your question. What? Where? Are you happy from this line to this line?
So once you have x squared plus 16 equals
Yeah.
25 divided by 9 times x squared, how do you get
Yeah.
the next line below?
So what you do is you take that guy and you subtract 1x squared from it. So you take that guy and you subtract 9/9 from it. You get 16/9 x squared.
Okay, all right.
Or you just do it in your calculator. You just do 25 9s, take away 1 and let it figure out. At this point here, would you agree that x equals 3? Are we good? Now, what does that mean? Doesn't that mean you actually do build straight to there? Because if x is 3, won't it mean here? So, there you go. The solution is build from the oil rig straight to the refinery. Now, if I had changed my story and changed that to say, oh, some really expensive, like 50 million a mile, right? So if I made being in the water really expensive, wouldn't the answer probably be get straight to the land as quick as you can, save some money? So the solution probably would have ended up being straight to A and then down. if I'd picked a number a little bit bigger than that, but not as horrible as the one I just given, I could have made the pipeline end up anywhere. So where the pipeline hits land is really how much these two things interact. If you make one of them really dear, you'll force one solution. If you make the other one really cheap, it's equivalent, you'll force another. If you play about with them, different things. This is a big thing in what's called networks. Networks is just really the part of math with how do you connect things together? One of its uses. Can you imagine how helpful it would be if you had a way of really finding out the cheapest way to go from A to B? It doesn't need to be pipelines. Can't you do it with electric cables, right? Or gas lines or roads, right? Suppose you had 5 places and you wanted to connect them by roads. What would be the least amount of roads that you could get all the places, you know, from one to the other connected? And we are finished for that part, but not for today. So let's move on to our last section. Oh, before I do that, is there any more questions on the ones I just did? Every question is going to be unique, guys. So just because I've covered some doesn't mean every possibility has been seen. So our last section then. Here's a puzzle for you. I have a function f of x. I'm not going to tell you who he is. But when I differentiated him, I got 6x cubed plus 4x squared minus 7. What was f of x? That's essentially an antiderivative question, which says, look, if you know the derivative of something, can you actually find what the starting function was like? Kind of like undoing the differentiation process. And that you got to be careful about because it's easy to fall into little traps.
So is this kind of similar to taking the inverse of functions and inverse of trigonometric functions?
It's an inverse of a process. So in the big family of undoing things, yes. But this fella gets the antiderivative process. It's a little bit different in the sense that, you know, the solutions are a little bit less obvious than undoing an x squared and getting square root of x. But it's in the same family. So I'm going to show you some examples of solutions. If you had 6x squared as your derivative, wouldn't the original function be 2x cubed? Let's check it out. If you do the power rule in that, right, you multiply by the power and you just by 1, wouldn't you get 6x squared? You agree that works, right? So if the derivative is 6x squared, the original function is 2x cubed. But couldn't it also be 2x cubed plus 7? Couldn't it also have been 2x cubed minus 3? Couldn't it just have been 2x cubed? Aren't there lots of answers whose derivative is 6x squared? So how do we cope with the fact that there are going to be more than one possible answer? You write it like that. And C as a name, it's called the arbitrary constant. And it represents the +4 or the +42 or the +0 that you might get. Suppose I had 10x to the 10. That's its antiderivative. Suppose I had that function, that was the derivative. Have you noticed they all have a plus c at the end, so you just get used to that. Every single one of these examples, I've now found its antiderivative. That's what we call this guy here. Problem is, how do you go from the question to its solution? Well, this guy generated that piece of the answer. This guy generated that piece of the answer. And this little fella here generated that piece of the answer, and you always get a plus c. Has anybody seen a pattern yet between this function and its antiderivative? If you do see a pattern, can anybody tell me what the antiderivative of this is? So what function would I need? If I differentiated, you'd get that. And I'm putting in the plus c for free.
Two-thirds x to the 6th.
And you're quite right about 2/3. I'm just going to write it as 4/6 for a minute. Do you see what he just did there? How you got from here to here? You want to put it in your own words? What were you thinking when you came up with that answer, which is correct?
First, there's a power rule. Normally, we take the exponent and multiply it towards the coefficient. In this case, we divide. So we go backwards.
So essentially, you add 1 to the power. So 5 becomes a 6. And then what do you do with that power? Well, you don't multiply by it. You divide by it. So we call that, unsurprisingly, the power rule. So the power rule for, I know I'm changing the names on you, integration. Antiderivatives are just another version of integration. So the power rule of integration says the following. If you have a function whose derivative is ax to the n, right? Like 5x cubed, 4x squared, something like that. Then the original function, so that's the antiderivative, f of x, is add 1 to the power and then divide by the new power. So that is your undoing process. That's how you get antiderivatives. Let's put it into practice. I want to do 3x to the 5, take away 2x squared, plus 4x minus 7, right? I want to find what the original function would be, the antiderivative as we call it. Actually, later on we'll just call it the integral, but right now it's the antiderivative. Each one, add 1 to the power, and then divide by the new power. So this one gets you a half x to the 6. Next one, add 1 to the power, you get x cubed, and divide by the new power. Add 1 to the power. Well, technically there's a 1 there, so when you add it, you get 2, and then divide by the new power. And the only funny one is, or strange one, I guess, is when you have to do numbers like -7 or +2. What's the answer going to be when the thing is a number? What's the antiderivative of a number?
Just add X.
Just add an X. And that's how I do it. Technically speaking, isn't that X to the 0 and then you add 1 to the power and then you divide by 1? But I just find it much easier to say numbers get you number with an X. And of course you finish with your plus C's. And that's called a power rule. And what that does is it allows us to find antiderivatives of any polynomial you like. You just add 1 to the power and then divide by the new power. So far, so good?
So
Well,
then,
that's not... Mhm.
so then probably an easy way to remember it then, when you look at the original equation, you know, f prime, maybe so you don't miss it, 7 x to the 0.
Yeah.
So you have something to add.
Yes, that is definitely one way to look at it. I'm just lazy. I just know, you know, I know when you get numbers, you just tag an X on, and for me, my brain, that's the quickest. Well, let's try. Suppose I tell you the derivative is 3e to the x. And I want to find its antiderivative. I love the e to the x. It's such a nice function to do anything to. What's the antiderivative of 3e to the x? You may be
I'm
saying
going-
something. So again,
I'm gonna go with its e 3 to the x.
and it is, well, plus c, of course. Well, think about it. Can you check your answer by just differentiating what you think the answer is, and you should get back to there? Would you agree if you differentiate 3e to the x, you get 3e to the x? If I was doing this question, remember the original was this guy. If you differentiate each of these guys, don't you get back here? So it is easy to check a derivative or an antiderivative. Just take your answer and differentiate it. So I like e to the x. Would you agree it's the easiest one to find an antiderivative of? It's the same guy you started with. How about,
So on the 3e to the x, couldn't the
Mhm.
original function be e to the 3x?
no, because if it was e to the 3x, when you differentiated it, you'd get e to the 3x times 3. You wouldn't get that.
Oh, that's right. Okay.
How about trig? Now, to do trig, you have to remember what derivatives are and then work backwards. So what function has a derivative of secant squared?
Tan.
So that would become 2 tans because of that. What function has a derivative of cosine? Sine. Now, shouldn't I check it? If you differentiate 2 tan, do you get 2 secant squared? Yep. If I differentiate, that looks weird, but if I differentiate 5 sine x, don't you get 5 cosine x? Agree? So I know it's right. Okay, let's put everything together in a package. I want to do 5x to the 4, take away 2x plus 3 plus 2 sine x minus 3 e to the x. Right, so that guy has got a little bit of this and a little bit of that, right? It's got quite a few things. If you want to find its antiderivative, shouldn't you just take each one on its own merits and get its antiderivative? So it doesn't really matter what else is going on, just what it's doing. Right, this guy would be the power rule. So you add 1 to the power, and then divide by the new power. So you get x to the 5. So that's good. this one, power rule. Add one to the power, divide by a new power. That works out nice. I like just remembering that 3 gets you 3x because it's less hassle. Be careful. What is the antiderivative of 2 sin x?
-2 cosine x?
Yeah. You notice that, guys? Do you know the most common mistake in antiderivatives that I see is people calling that 2 cosine x. And that's because if you did differentiation, it is 2 cosine x. But if you do an antiderivative, doesn't things kind of get turned upside down occasionally? And that's one of them. Now you can always check. If you differentiate -2 cosine x, don't you get +2 sin x? So you know that's the right answer. And this guy here is my friend. So we'll call it good. And this is the beginnings of Calc 2, where you are trying to undo differentiation. And that process of undoing it is called finding antiderivatives. And that's what we've been doing. I just thought of one, last one. Be careful. What is the antiderivative of 10 over x?
10 times the natural log of the absolute value of x.
You remember differentiating logs, you get 1 over x, so 10 logs gets you 10 over x. And I almost forgot. Plus c. Right, last name down. And hey, we're already into our last section. So with a bit of luck tomorrow, we'll get that one done. That gives us Wednesday to revise for the final. And then Thursday is our final. So we made it. Bye-bye for now. I'll hang about for questions.
So I'm guessing every single time we do since we don't know how to find, I guess, C for like the constant before, we just always add C for the antiderivative.
Yeah. The only time that you wouldn't do that is that if they gave you a question and they said, oh, by the way, f of 0 is 42, then you could find out what number C is. But in general, you just say a plus C and that's it.
Okay, that's easy enough.
Yeah, just a rule. Putting a plus C, everybody's happy.
All right, you have a good one.
You too, Matthew. I'll see you tomorrow.